Okay, then I told you that I want to speak about orders of magnitude. And for now, I'm starting with orders of magnitude at the global scale. So how much water there is on the Earth. First of all, total water reserves. The number is given in square kilometers. The number that you have absolutely not to remember is given here. What is interesting to remember is not the total number, but the subdivision of the available water resources between different categories of water. This, I think, is more important. And I think it's important to say that we already know this, but quantitatively say that 97.5% of the total water is given by salt water. The salt water is mainly concentrated in the oceans, of course, but there is also some salt water in the lakes. Typically, a lake becomes salted when there is no a fast exchange of water inside it. Like the Dead Sea. The exchange of water takes a long time, and therefore with evaporation that is very relevant, you have an increase of concentration of salt. So we have a very limited percentage, 0.01, of salt water in lakes, and about 1% of the total salt water in groundwaters. This typically happens close to the sea. There is salt water intrusion from the sea to groundwater. And this is a phenomenon that is really to avoid. Because of course, salt water cannot use for irrigation and needs to be desalinated in order to be used for human purposes. Okay, then let's concentrate on the 2.5% of the fresh water. And the fresh water is present in different forms. What is important to know is that 30% of the fresh water is stored in groundwater reservoirs. Then we have almost 70%, almost all the remaining fresh water that is stored in glaciers, permanent snowpack, and permafrost. So this is a kind of water that is for us more difficult to use, of course, because we are talking about permanent storage in solid phase of water. Then we have a very limited percentages in other forms like lakes and marshes. Marshes are paludi in Italian. It's about 0.3%. Then we have soil moisture, 0.05%. Atmosphere, 0.24%, rivers, and biosphere. Please note that even if the percentage of water that is stored in rivers is very limited, nevertheless, rivers are very much important for water supply, because the water stored is permanently stored in the river is not very significant, but the water flowing in rivers is a significant percentage of the water resources that we used for civil purposes and irrigation. So the storage is limited, but the volume of water that flows across river is very significant. Okay, let's try to move forward and let's have a look at the water cycle. The water cycle also called the hydrological cycle, is something that we well know from the primary school probably. And, but it's important to focus on it a bit at the beginning of this course, because there are some issues that I want to highlight. First of all, let's consider, just for your curiosity, that hydrology, it is also defined as a science that studies the water cycle. But modern hydrology, indeed, studies something more than just the pure water cycle, because hydrology is also related to chemistry of water, to water quality, which are issues that are not directly related to the water cycle. So when I say water cycle, hydrological cycle, they are usually treated as synonyms, but accordingly to modern concepts, hydrology is meant to include greater variety of processes than just those that are included in the water cycle. So the water cycle, basically, we will know that from the oceans or from water in the liquid phase that is stored on the earth, through evaporation, water passes to the gas phase and goes into the atmosphere. And in the atmosphere there are some transport processes of water in the gas phase, in the vapor phase, or water already in the liquid phase, because in the atmosphere then there is condensation. So in the atmosphere we have transport processes that bring water around the whole Earth in the atmosphere. And water condensates in clouds, from where, under given conditions, water falls in the form of rainfall and snow, and then reaches again the earth. This is what we all know. When water reaches again the earth, then starts traveling again downstream towards the oceans. So this is something that we all know. But there are, as I said, some issues that I want to highlight. First of all, I will give you in the next slide some numbers in order to give orders of magnitude for these fluxes. But I want to highlight, first of all, that we are mainly concerned on Earth's processes, not atmospheric processes. Atmospheric processes are usually dealt with in meteorology and climatology. The main domain of the hydrologist is given by Earth's processes taking place on the Earth. And also for an engineer, in our case, this is our main domain. Then, there are some things that we don't know about what happens in this cycle. A lot of things, because as I said, hydrology is a young science, hydrology is difficult to observe, and we have a few data only. So, for instance, we still don't know how water reaches the river after it is rained and landed on the earth. We still don't know how this travel from the Earth's surface to the river takes place. We know that it happens. We know this because we observe water levels in rivers increasing after a rainfall, and suddenly increasing, I would say, let's say quickly increasing, which means that this travel time from the Earth's surface to the river takes not much time, at least for a significant part of the water volume, but still we don't know what happens from the time instant in which a drop of rainfall lands on the Earth's surface to the time instant in which we observe water in the river. So there is, at the beginning, classical hydrology used to make a subdivision at the level of the topographical surface. It was assumed that part of the rainfall flows on the topographic surface in the form of what is called surface runoff, and the remaining part, it was assumed that infiltrates and travels underground towards the river. So in classical hydrology there is a subdivision at the level of the Earth's surface between surface runoff and groundwater runoff, infiltration and then groundwater runoff. But actually this view is now questioned, because you may go over a hill slope, a versante it is called in Italian, during a very heavy storm, and you probably will not see any water flowing on the surface, because it was observed that actually in many cases you see the river level rapidly increasing with no water flowing on the hill slopes. And this means that water actually doesn't flow on the Earth's surface. Water infiltrates. Probably most of the rainfall infiltrates. But given that the travel time is very reduced, given that the trip is very quick, we can conclude that it's unlikely that water goes in the deep underground, because to infiltrate in the deep underground would take longer. So now the hypothesis is that probably water flows in the immediate underground, so originated what is called hypodermic flows. Hypodermic, which is hypodermic in Italian, means that it's just below the surface. But actually, this process is not known. So this is an assumption that is being tested by using tracers. Tracers means that you release in the water some kind of tracer like salt or like isotopes, and then you drop the water on the surface. Water infiltrates, and then you go to the river and notice when your traces reach the river. So you have an idea of the travel time, and also you may have an idea of the flow path, which means the way that the flow followed to reach the river. So this assumption is being tested, but still we don't have really clear indication and a clear perception of what happens. There is one thing that we may consider. If you go over a roof during a heavy storm, like the roof of your house, there of course you see water flowing, because the roof is impervious, water cannot infiltrate, so you see water flowing. But actually, even if the roof is completely impervious, and even if you go there during a very heavy storm, you see that the water height, the water depth is very, very limited. It's you really have to see very well for realizing that water is flowing. So this means that in the hill slopes, water can indeed flow on the Earth's surface, but we could not see it. Probably it flows, but given also that in the hill slope there is some grass, there is some coverage of the soil, maybe that water is flowing, but we cannot see it, because it's difficult to see water flowing, even on a roof, on a completely impervious surface. So basically, what is important for us to know is that there are many things that we still don't know, and we are talking about the Earth's surface, which can be observed. Think of the underground, of this form of flows, infiltration, percolation, soil moisture, processes that are driven by soil heterogeneity, and not to speak about the groundwater flow, with transit time that may take years, may take even thousands of years. Of course, these processes are very poorly understood. Of course, there are assumptions. There are mathematical models, even mathematical models trying to reproduce what happens, but still, these models are characterized by a very relevant Uncertainty. This is an important keyword in hydrology and water resources management. Uncertainty. For an engineer, this is an issue that deserves to be taken into consideration. You have to think that hydrology is not like structural engineering, where the loadings can be determined with much precision. And also the size of beams, the size of the structures can be determined with a very satisfying precision. In hydrology, uncertainty is very relevant. When we talk about water flow in a river and we take a measure, the error is in the range of plus minus 20%. And if it is, you are lucky, because in many cases you may exceed this range. This means that the decision process should be articulated accordingly. You have always to consider the presence of uncertainty. So safety factors, which are also called in English allowance for freeboard, are very important. And also when you communicate with the users, with decision makers, it's very much important that you make clear the presence and the meaning of uncertainty. Because there is some misunderstanding, frequent misunderstanding between engineers and end users. End users sometimes are used to speak with engineers, and they implicitly assume that your reply is certain. Because of course, when one guy asks you to size a beam or an house, of course they expect that you give a certain answer. So, for analogy, many guys who come to you and ask you to size a water supply system, an aqueduct or a dam, they may assume that your reply is certain. And this misunderstanding has originated many problems and also some tragedies. So it must be made clear the presence of uncertainty in hydrological design. And I can tell you that there is a debate ongoing in the scientific community about the most effective way of communicating uncertainty. And there are some scientists who are convinced that if you communicate uncertainty, you undermine the confidence. Undermine means you make lower the confidence of end users in your opinion, in your studies. So there are indeed some people who are convinced that it's not a good idea to communicate uncertainty to end user. But my personal opinion is that the most important thing that a scientist and an engineer must convey is the truth. And of course there must be an ideal way of communicating uncertainty, but not communicating it is not, in my opinion, the way to follow. Okay, water cycle, some numbers. These numbers are not really all to remember. Try to remember maybe for your interest as the most important ones. It's very difficult that in an exam I ask a question about what is the amount of evaporation from the ocean with respect to the land. So don't take my interest in the order of magnitude as an invitation to you to learn all these numbers by memory. Absolutely not. Okay? So these numbers here are given in relative form, and relative form means that precipitation on land is equated to 100, which is not a real number. It's just a reference number. Okay? This is not the real number. I will give you some real numbers later. So if we assume that precipitation on land is 100, then we have evaporation from the ocean, which is 424. And precipitation on ocean is 385. You see that there is a difference of 39, which means that 39% of the amount of rainfall on land is a difference between evaporation and precipitation over the ocean. 39, in fact, you see that is the amount of the moisture flux from the ocean to the lands, which, if summed to an amount of 61, which is evaporation from lands, then we obtain a total of 100, which is what we expect, of course. What is important to note here? It's important to note that precipitation over the oceans is about 4 times precipitation over the land, which is to be expected because you have a higher evaporation over the oceans, which means an increased precipitation. Okay. Let's have a look at this number here. 38 is surface outflow, which compensates 39, which is moisture over land. So we have in the atmosphere a flux of water from the ocean to the land, which is balanced by the flux of water from surface outflow and groundwater outflow, which is 1. What is groundwater outflow? Is water that flows in the ocean directly from the ground without passing from the river. Just to give you another idea of uncertainty, I want to speak some more about this groundwater outflow, which is quantified here, but which we actually do not know. We don't know the amount of water which from the underground flows directly into the oceans. We only know that it's a limited amount with respect to rivers. And to give you the feeling of how much this issue is important, because you may think that it's not important to quantify this groundwater outflow. For what reason it should be important? Because it's water that I cannot use, or water that I don't see, in any case. And also it's a limited flux, so I may conclude that it's not important to quantify it. But indeed, this is a sign of the fact that we don't know these processes. And it's important, this fact, the lack of knowledge, and I explain you why. Once I met at a conference an oceanographer, a person who makes mathematical models of the oceans, of the circulation in the oceans. And this is very much relevant for studying climate change. You know that climate is strictly related to ocean circulation, like the Gulf Stream, the streams in the oceans are very important for determining climate. And this person was setting up a mathematical model of circulation to support the development of global circulation models, which are used to predict the future climate. These are the kind of models whose results are mentioned by the media when they speak about climate change, about future climate. And they say models are predicting an increase of heavy rainfall and a decrease of the mean rainfall, which means that we will get more exposed to flood risk and more exposed to drought risk. Parenthesis, usually when media report to you prediction, they report only the negative prediction. They don't tell you, oh, models say that in 50 years we will have a lot of water and we will improve our condition. This is not the kind of interesting news. Interesting news are those related to worsening of the living conditions. And this is a bias of media, of course, but you can understand this bias very, very easily. So these models that predict the future climate conditions, which are often mentioned, are based on also on ocean circulation model. And this person came to me because he said, I have a very good model, very refined, which I really trust, but I need to know how much groundwater I get from into the oceans. So he looked for an hydrologist explaining these water fluxes from groundwater into the ocean, because he said that they are very relevant in my model. So if I ignore these fluxes, my model gives a different result with respect to a situation in which I consider these fluxes. So he said I would leave a detailed description of this. And I replied that this is simply impossible at the present state of knowledge. We can give you a global number, maybe, which is anyway approximate, but we can't tell you exactly the fluxes that are coming, where and when from the different continents. Of course, we can tell you the fluxes from the rivers, and he said, I already know that. But we are not able, at the current state of knowledge, again, to describe these fluxes from groundwater to ocean. And he said, okay, but this is really a big problem, because the output of climate models will change if you make changes in these fluxes. I'm telling this issue to you to imply, one, that the prediction from climate models are affected by much uncertainty, which is not conveyed. It's very difficult that the media tells you, okay, there is this prediction, but it's highly uncertain. This is very difficult because it's not an interesting news. An interesting news must present certainties, not uncertainties. And second, this part of the process that we don't know is important. Even if the water flux is not very much relevant, is important. Okay. Next time I will bring with me also the battery charger of the PC. Some more numbers. I'm not entering into the details of these numbers, and you may find here some of the numbers that we already found in the previous slide, even if the source is different. And let's see, for instance, at rainfall, total terrestrial precipitation, which is 111. This is a real number, meaning that the average global precipitation over the Earth is about 110 centimeters, about global precipitation. This is a number that is interesting to remember. And how much water falls on average over the Earth? About 1 meter per year. And this is not incidentally, this is also the mean average rainfall, roughly speaking, over Italy. Italy is placed at a latitude which makes rainfall over Italy comparable to the global average of rainfall. Over Italy we have a little bit less. Rainfall over Italy is ranging from 80 centimeters in the south to about less, let's say 60 centimeters in the south, 80 centimeters here. And if you go to northern region like Friuli, which is the rainiest region in Italy, you get an upper level, a maximum level of precipitation in a year that is about 2.5 meters, 250 centimeters. So this is the range of variation of rainfall in Italy. You may find some regions where the rainfall is even lower than 60 centimeters, but the order of magnitude is like so. If you don't understand something, please ask me, okay? Because sometimes I see faces that are a bit, and so probably it's my English that is not really well understandable. Okay, and you see a difference, a distinction between snowfall and rainfall, which is not very relevant for us. And here you see precipitation over the ocean is almost 4 meters, and confirms what we already depicted in the previous slide. And also you have an indication of other fluxes, evaporation, and net water vapor transport in the atmosphere. And there are here, numbers are expressed in sorry, this is, let me think about, okay, I said centimeters, but indeed these are expressed as total volume per year. I said centimeters per year. Instead, it is total volume. So in order to get the fluxes in centimeters per year, we need to divide for the related surface, which makes anyway number consistent with what I anticipated to you before. So it's comparable. When I said that it's about 1 meter of global, it's correct. Okay, it's correct. I didn't notice that there was a different unit of measure, but what I anticipated is correct. And okay, this is a picture. Let me see if there is something else that is interesting to. No, I would say one thing. One thing is interesting, which was already given by the previous picture. Here you have a quantification of the river flow. River flow, which is significant. When I said river storage is not significant, but river flow is significant, you can see from these fluxes that indeed is significant. And you have an indication here of 45.5, which is given in 1,000 square kilometers per year, global indication. And you can see from here that, again, the storage is not significant, but the flow is significant. Okay. Now, let's talk about problems related to water. So, with the quantification, we have finished. Now let's talk about problems. And I will mention just two problems, floods and droughts. We will concentrate on droughts rather than floods. Droughts in Italian is magre, water scarcity. Because floods are usually, I already mentioned to you, usually not treated within water resources management. But indeed, floods are a consequence of excess of water. And they cause extensive damages worldwide, which makes floods one of the most important from an economical point of view among the natural hazards. One of the most important natural hazards. You see that there is an indication here. During the 5-year period, 1991 to 95, floods-related damage totaled more than 200 billion of US dollars. Billion in Italian is miliardo, to be clear. And so, globally representing close to 40% of all economic damage attributed to natural disaster, which means, again, 40% of the damage of natural disasters is given by floods. In the United States, annual flood damage runs in the billions of dollars. Miliardi di dollari, which is about, the conversion, dollars, euros. You can think about 1-1. Improved prediction of floods could reduce this cost substantially, in addition to reducing flood-induced loss of life. So floods are very important. Now, droughts. Droughts is given by a series of events, of situations. And drought, how do we define drought? Drought is a temporary reduced availability of water. Which means that if you are in a place and you expect an average water availability, drought means that for a certain period you have less than average water availability. So drought is a temporary situation, which means that there are two main descriptors of drought: intensity and duration. Drought is different from water scarcity, which is a permanent water shortage. So I may live in a water scarce area, but I may not experience a drought. Drought means less than average. Of course, the consequence of a drought is more severe in water scarce areas. Because if you have plenty of water, of course, if you have less than average, it's still a drought, but it's not so severe with respect to the situation in which you permanently have a shortage of water. So water scarcity means permanent shortage. Drought means temporary shortage, temporary less than average. Now, the problem is that population in water scarce areas is increasing, even more than in water rich areas. You can see here a sketch of the dynamics of population in US, and you see that if you look at the percent increase of US population, you get a curve which shows you that the percent increase in waters in the southwest, which is arid, this percentage increase is even higher.